We will now continue to use Gauss's law to find the electric field due to extended charge systems. And let's now look at this case. Field due to a uniformly charged sphere. Well, when we left off the last part of this lesson, we calculated the electric field due to a charged shell. Now, this is different. This is not a shell. This is a solid sphere. That is, there is no space in there. There is complete material all over the sphere. Field due to a uniformly charged sphere. Alright, consider a sphere of radius r carrying a uniform volume charge density. See, this time you need to consider charge per unit volume because we are considering the entire volume of the sphere. And so the volume charge density is rho. Well, if rho is the volume charge density, what is the total charge on the sphere? The total charge on the sphere will be rho multiplied by the volume of the sphere. What is the volume of a sphere of radius r? Will be 4/3 pi r cube. Don't forget that. We will be using this as we go on. So, it has a charge density rho, so that the total charge Q on will be Q equal to 4/3 pi r cubed rho. The volume of the sphere multiplied by charge per unit volume. For electric field at any point on the sphere or outside the sphere, this charge Q can be considered to be a point charge. You see, just like the shell, the electric field on the surface of the shell or any point outside of it, the amount of charge on the shell behaves as though it is concentrated at the center. In the same way, for electric field at any point on the sphere or outside the sphere, this charge Q can be considered to be a point charge concentrated at the center. And the electric field anywhere where r greater than the radius is given by what equation? KQ over r squared. And if you replace your K by 1 over 4 pi epsilon naught, it becomes electric field at a distance r where that distance r is greater than the radius. In other words, greater than or equal to at a point on the surface of the sphere or anywhere outside it, the electric field will be ER equal to KQ over r squared, where K is 1 over 4 pi epsilon naught. So this is for the distance r greater than the radius of that sphere. So this is the sphere of radius r. At any point outside or at any point on the sphere, the electric field will be 1 over 4 pi epsilon naught times Q over r squared. Now, to find the field at a point inside the sphere. Now, this time, remember, don't confuse again. The field inside a charged shell is 0. This is not a shell. This is a solid sphere. So, in order to find the electric field at a point inside the sphere, distance r from the center, we construct a Gaussian surface. What kind of a Gaussian surface? The Gaussian surface will be a spherical surface that will enclose a spherical volume inside that surface. So we construct a Gaussian surface of radius r. So this is the sphere. We construct inside that sphere a spherical shell of radius r. and this is the Gaussian surface, and we want to find the electric field at a point on the Gaussian surface. Remember, the Gaussian surface is constructed in such a way that the point where you want to find the electric field is on the Gaussian surface. So we want to find the electric field ER at this point on the Gaussian surface. Alright, that's simple now. You can use Gauss's law very easily. If E sub R is the field at any point on this Gaussian surface, what is the net flux leaving this surface? I'm sure you can now tell me. What is the total flux leaving that Gaussian surface? The Gaussian surface is a sphere. What is the area of that Gaussian surface? Will be 4 pi small r squared. And ER is the electric field, means flux per unit area is E. So if you multiply this E with the area 4 pi r squared, that is a measure of the net flux leaving the Gaussian surface. So phi net equal to 4 pi r squared, which is the area of the Gaussian surface, multiplied by E sub r, which is the electric field at a point on the Gaussian surface. Now, by the total charge inside the sphere, what is the total charge inside the sphere? Inside this sphere, you see the Gaussian surface encloses a sphere of radius r. What is the volume of that sphere? The volume of this sphere is 4/3 pi r cube, where r is that small r. And if you multiply that volume with rho is the volume charge density. So the total charge inside the sphere of radius r is Q inside. What does Q inside mean? The amount of charge inside that Gaussian surface is the amount of charge inside that small sphere of radius r. Will be 4/3 pi r cube, the volume of that sphere, multiplied by rho is the volume charge density. Now, if this is the amount of charge inside, what does Gauss's law say? Gauss's law says that the net flux crossing the Gaussian surface equal to 4 pi k times Q inside. There we are. So, phi net equal to 4 pi k times Q inside, or 1 over epsilon naught times Q inside. Remember, both can be used at any time without any problem. 1 over epsilon naught times Q inside is the same as 4 pi k times Q inside. So 4 pi r squared times ER is the net flux. And that net flux must be equal to the total charge. That will be 1 over epsilon naught times the total charge inside the Gaussian surface. The net flux equal to 1 over epsilon naught times Q inside. And now, let's simplify that. Well, we can calculate or solve for ER from there. After, you can see pi and pi goes, 4 and 4 goes, r squared on the left will go with r cube, leaving an r there. So what will be ER equal to? Can you solve for ER from there? ER equal to rho divided by 3 epsilon naught times that r. Remember, the r squared cancelled with r cube, leaving an r there. Like this. You have a 4 pi on the left cancelled with 4 pi. R squared on the left cancelled with r cube, leaving an r. So ER equal to, you have a rho divided by 3 epsilon naught times R, and this is the expression for electric field at any point inside the charged spherical object. That is not a shell, it's a solid sphere. Okay. Now the field inside the sphere varies directly as R. What does that mean? That means inside the sphere, the electric field at the center is 0. When this R is 0, the electric field is 0. And as you move away from the center, the electric field increases. The electric field is the maximum at the surface of the sphere. What is the electric field at the surface? KQ over the square of the radius. And now if you go outside the sphere, the electric field will decrease. Alright, let's draw a graph representing that. The electric field at any point inside the spherical charged object. Now the yellow is the spherical charged object. Any point inside, the electric field is rho over 3 epsilon naught times R, and at any point outside it is 1 over 4 pi epsilon naught times Q over R squared. This means that the field increases linearly from the center of the sphere until it reaches the surface. It has a maximum value at the surface where R equal to the radius, and then decreases away from the center where R is greater than the radius. So this is how the electric field varies inside a solid sphere. The electric field increases from 0 to a maximum. Where do you have the maximum electric field? We have the maximum electric field at the surface, and as you go away from the surface, the electric field decreases, becoming 0 eventually. Okay, let's now use this to solve a problem. A sphere of radius 6 centimeters